And then I think that it's very good in the afternoon if it's possible to do this thing with the computer, so we link one of them. I hope it works. Okay. So now to the challenges I started yesterday with, and the way I see it is that the main challenges in to design a power system is when you have a large amount of solar and wind power, is to keep, of course, the continuous balance, which you always have to do in a power system. But then you have these two very specific situations, and that is, of course, that when you don't have any wind and solar power, this is more a dimensioning issue, because let's say you have a huge amount of wind power, but you don't have any wind. That is exactly the same thing that how do you run a power system without wind power, which is an ordinary power system. So of course you have to have enough resources for this. But this is very much discussed as a challenge more from the economical point of view, because the question is that, let's say you have a lot of coal power. What is happening if you come with wind power is that you will operate the coal power on very much lower amount of hours. So they become more costly. So in some way you must manage peaks, and these peaks can be sharper, which is a challenge. I will show you in a while what it means in an example, in reality. The other one, which is a bit more specific, is that when you have so much solar and wind power, so you in reality are covering the whole demand with solar and wind power, then of course the challenge is more fundamental challenges, because then you have the challenge of inertia in the system. You don't have controllable units in the same way as otherwise, and you have very low, for example, also. So this is a more, you can call it technical, specific issue, while this is a standard issue, but it's very much discussed that you cannot replace everything, because there are, of course, situations when you don't have so much solar and wind. So these are the way I see it in general is that if you are thinking about the power system in the future, and you want a huge amount of solar power, you first have to think about how to solve this issue. Okay, I want to have a lot amount of solar and wind power. Okay, when I don't have it, what do I do? Of course, you need some kind of resources. You need to have gas turbines or something as reserve power or whatever, or you need to have transmission lines to your neighbors where it may be more, or interconnect all the states, so you have at least wind somewhere in the system or something like this. So the step one is that you must have enough resources in the power system in order to do this. What is important with this, to start with this one, is that then you know which resources you have in your power system, because you have to have all these resources. And then you should know, of course, that when you come to this situation, you have these resources. For example, what is discussed in Sweden, that let's say that you don't have any wind and solar. What do you need? Perhaps gas turbines. Gas turbines have a synchronous generator. What you can do in a gas turbine is that you can disconnect the turbine from the generator, and then you can run the generator. You have this technology. You can buy it already today from General Electric. They have this kind of thing, and that means that, of course, you can disconnect in these gas turbines. If you buy that type, you can disconnect the generator, and then you have a synchronous machine running in the system, and then you have both inertia. It's not so much if you disconnect the turbine, and then you have a voltage control and so on. So it's important to start with this one, so you really understand which resources you have in your system. Next step is, okay, how do you handle this? Then, of course, you must have enough resources to handle this situation. And then the question is, okay, if I can handle that, then I probably can handle this automatically. So I think you shouldn't start here when you are thinking about the future. You must think about which resources do you have, how do you control them to handle this one, and then the question is this really a problem? It may be, but I'm not so sure about that, because you have all the resources already. So, because sometimes people start with this without thinking about this. I've seen a bit too many reports where people said, okay, but what do I do when I have a huge amount of wind? Yeah, but you have a lot of other resources. I just talked to people from NSOE, which is the coordinating organization in Europe. And they said that they are a bit afraid of this one. But then I said that, yeah, but what kind of other resources? Yeah, but we want to get rid of the other resources. But then I said that, yes, that's okay, of course, correct. But what do you do in this situation? You cannot only talk about this one. Because this is the challenge when I talk about this. Here I talk about megawatt, of course. This is megawatt changes. This is megawatt in a specific situation. This is megawatt in a specific situation, while this is dynamics. So, if you go into a bit more of a detail, handling of the continuous balance, which I see that, yes, that is the main issue. And everything is about, of course, keeping the continuous balance. But the main challenge is that there must be ramping capacity, because you get higher ramps that the other power plants have to cover. The issue is also very much that it will be more uncertainty in the system. Because today you have the demand, which is a bit uncertain, but not so much. The other uncertainty you have currently, if you have a conventional power system, is that you have outages. But here, with more solar and wind power, you don't know exactly how it will be in 5 hours. On the other hand, I think solar power is rather predictable here in India, I think. In Sweden, it can be that, I think when I showed you my own power plant, my solar power home, it's very different from day to day. Here it's perhaps more predictable, the solar power, but wind power, I think it is everywhere. You never know how windy it is and so on. So I think wind power at least, so solar power may be better here than in other countries from the forecastability point of view. And then of course larger interconnected areas reduces the overall variation. Not so much, that's what I talked about also yesterday, perhaps more in the afternoon. This is mainly an important issue for wind power, because it's not, the wind is very different in different areas also, I'm sure, in India, while the solar power is normally varying around the same way. It depends on if the country is very wide from east to west, then you have a slightly difference in the solar power. But this is mainly a big important issue for wind power, to have a large grid. Then you have this I will go into more in detail later. 3 challenges, and then the problem is the low wind and solar power production and high consumption. This is of course an issue, that is that you need to, if you don't have enough capacity, then you have to curtail people. And this is called the capacity adequacy, that we should have enough capacity issue in the system. And this means of course that there must be in some way enough capacity in this situation, because otherwise you have to curtail load. Then I think it's important this with curtail load. You have of course 2 types of curtailing load. One is that people say that I don't want to pay too much, please curtail me if the price is too high. That is flexible. On the other hand, when I say curtailment here, I mean that you curtail people without asking them that they are prepared to be curtailed, and they are prepared to pay the price that you have at this situation. But to get enough capacity, of course, to have production, you can have flexible demand. And here I talk about import, but that is not interesting from India point of view, but from Indian states point of view, it can be of course important. But because India is the same, I was in China talking about this. And then of course the issue in China is that, China can never rely on import on electric power. It's absolutely impossible. It's the same as US, for example. Big countries cannot discuss this. But then if you talk about states, then of course can think about this. And Sweden is more a state in this case. So there must be enough capacity. The issue is very much that this can happen very rarely. For example, in Sweden, the peak demand, I don't know exactly how, I have not seen any data for India, but in Sweden, the big challenge is in reality that it can be extreme. We have a lot of electric heating in Sweden when it's cold. And there is a risk that in the country, it happens, let's say, 1 year in 12 or something, or even more rarely. And then, of course, if it happens in this situation and at the same time it's not windy, that can happen, but it's very rarely. Then the question is, what do you do? Because if you have electric heating at home and it's minus 18 outside and you just curtail the people, sorry, that's not so nice. But the question is very much these rarely used units, and I don't know exactly how it looks in India here, because I assume that you can get it very hot here, and then if you get it very hot, then you put all the air condition on maximum at the same time, because you normally have, if you go south, you have the summer peak where you have the air condition, and especially when you become richer and richer, then of course you get more and more air condition. You can see that in industrialized countries that are rather south, then you get an extreme peak just in the summer. On the other hand, if you have solar power, then of course you have a very nice correlation here. So of course you will get much more power when you have it. So from solar power point and in hot countries, this is perhaps not as a big problem, because exactly when you have the peak, you also have much more production from the renewables. So this may be not an issue for India, I don't know, but for Sweden it's a big issue, because it might happen that, of course, we don't have any solar power in the middle when it's minus 18, and it may be that we don't have any wind. So in the Nordic countries, this is classified as an important issue. Maybe not here, I don't know. And more transmission, of course, the need here. That was a good reminder. I must check. Yes. But then you have the other issue, and this is, I'm sure, will be an issue in many states, and that is when you have high wind and solar power plus an HVDC. That is, then you have a challenge, because the basic thing, I will come back to that, is this the fundamental frequency control in the power system. The frequency control is based on, I take some details around it, is based on that the instant balancing changes in the power system is handled by the inertia in the synchronous machines. And if you have only solar and wind power, and you have the type 4 generator of wind power, which you more have, then you don't have any inertia in the system. So that is very much, today, this is one of the more fundamental challenges you have in very much of the research, the new research that is coming in right now. What do you do when you don't have any inertia in the system? Because it's mainly keeping the frequency. Keeping the voltage you can do another thing. Of course, what you do today, we have discussed that earlier, that if you take away the central power plants where you have the synchronous machines and replace them with solar and wind power in the distribution grid, then you have, of course, a challenge keeping the voltage. But from the technical point of view, you can buy static VAR compensation, you can have capacitors and inductors which you are switching, which are keeping the voltage. So technically this is possible, but keeping the frequency is more challenging. There are certainly solutions. I don't say absolutely not that it's, but you don't get it automatically. You don't get it by building a huge amount of solar and wind power. You don't get something automatically that is keeping the frequency, because then perhaps if you take away all the conventional units with the big synchronous machine where you have the big H, which is the inertia, then of course you can get the challenges here. And then of course there must be enough primary and secondary control reserves. I will take this in a while and go into the details. So this is the interesting thing is that we are talking about high shares of solar and wind power, and the biggest challenge is when we have high shares of solar and wind power. You have to manage these situations. And in reality, what I will show you later is that certainly, if you have so large amount of solar and wind power, you will curtail it. And you do it everywhere. So I will just illustrate this with, now I see that okay, so this is unfortunately there is a point left there. It should not year 201. It should be 211, I think the data is from. Anyhow, this is the way the Swedish power system looked like. So we have a large amount of hydropower, and this is varying. This was a rather wet year, so we have rather much hydro. Then we have 40% of hydro, or 45. We have around the same amount of nuclear. These are, on the other hand, very old now. We have 12 reactors in Sweden, and they have decided to, no, we have 10 reactors in Sweden. They have decided to close down 4 of them up in the coming 3-4 years. And then the question is, when will the rest of the nuclear be closed down? And new nuclear is extremely expensive. It's much more expensive than wind power. So I think it's nearly double the price currently. There have been auctions in United Kingdom about nuclear power, and the cost is, what is it, 1 crown? It's 10 rupees per kilowatt hour. That was the cheapest bid they got. 10 rupees per kilowatt hour, guaranteed price, 35 years with increased price, increased payment according to inflation in 35 years. And if they got that payment, 10 rupees per kilowatt hour, then they were prepared to build nuclear. And I'm sure that wind power is cheaper than that, and maybe in India also solar power is cheaper. That's at least what is going on. So in Sweden, there was up to 2011, I think, around, there was a discussion to replace the nuclear with new nuclear, but that is today out of the question because new nuclear is just too expensive. So in Sweden, we don't have so much this conventional thermal units. Is very little. We have no coal power. We have some coal power in combined heat and power because we have a lot of heat. So we have district heating in Sweden, and because of that we have in combined heat and power. Then we have industrial production, and that is when you have a, I don't know how much common that is here, but I mean, if you have a paper mill, for example, what you take is that you take the wood, and then you take part of the wood you have for burning, and then you get a steam internally, and in this factory, and this steam is then used for electricity production. So it's in reality biopower, you can call it. So it's renewable energy in the industry. And I don't, we have rather big paper industry in Sweden, so there you get this renewable energy from the industry in reality. And it's, okay, it's not big, but it's still 5% of the Swedish production. And there you have synchronous machines, even if you take away the conventional units. That's important to remember. Sorry. So this is Sweden. We have, as I said earlier, we have only 10 million, so the majority of the people live down here, and then all the hydropower production is up here. So the challenge is, what is happening in Sweden today is that if we only look on all the wind power projects that are planned in some stages, and that means that then they are planned, this means that someone have phoned and say that I'm interested to put up a wind power plant, or it can be that I have got offers for wind power plants. It can be on different stages. But if you look on all these, there was a collection of the IDs of having wind power. The identified wind power is 100 terawatt hours per year, which is a huge amount of power. Today the size of this is 150. So all the wind power projects that exist, if you add them up, it's more than, it has all these. If you replace all the nuclear, and then you replace this, and you replace 50% of the hydro also, why should you? So in Sweden, there is absolutely no lack of resources when you talk about wind power. The issue in Sweden is more like we have wind nearly everywhere. We have wind here and here and here and here. The question is that today we don't know where it will come. And here we have a grid planning problem, and this of course you can have everywhere. I'm sure that in India, if solar power go down significantly more in price, you may get solar power everywhere, but you don't know exactly where. It may be in some states you will get it, but not in other states, and can you allow it in the local? And then of course it depends on in India. I'm sure that if you have different pricing structures, if you change the pricing structure from having a fixed tariff to something else, then of course, if you raise the tariffs for people, then it will be extremely smart for them to start to use solar power instead. And then you can get it very fast. If just the price, because the issue with solar, also with wind power, is that it's extremely fast to build. I mean, if you have a coal power plant, I mean, you have to plan for 5 or 10 years to just get it up, because you have the environmental and you have the area and the construction and so on. Solar power you get in some months. And this means that if you suddenly in India, I'm sure that if you start to liberalize the market and you want to have the price that is reflecting the cost, then of course you will raise the prices, and then suddenly people can start to build a lot of solar power. And then of course the challenge is how to manage the grid. So you have the same challenge as we have in Sweden, that wind power you can also get very fast. You order it, okay, when can I deliver? Half a year, something. But you can never say that, okay, I want a new grid, can you get it in half a year? That's not possible, because that takes time. You have to have the allowances to build the lines, to strengthen things and so on. So this is very much discussed also in Germany, for example, that how to manage all the renewables, which is very fast to build, and combine it with to expanding the grid in the right way. So, and the problem in Sweden is the following. Where will all this wind power come? Will it come here, or here, or here? And now the challenge have come now, which is of course very good, but it makes it more complicated, and that is that offshore has become much cheaper. So it may be that we will get offshore, and then offshore is here, while so the cheap offshore is here, while I think the cheap onshore is more here, because here is so densely populated, so it's not so easy to find places for wind power, while here it's here you can go in a train in 4 hours, you don't see a house. So it's just forest. I think 70% of Sweden is covered with forests. So the challenge is that we don't know. We have a huge amount of resources. They can come up very fast if they are needed, but you don't know where. So grid. Okay, now I have this. What I will show now is a power system which is 100% renewable, which is in reality what the Swedish Parliament have agreed on for Sweden. And it's more a backward calculation. It's more like this, that in Sweden we don't have coal power. People don't want to have coal power. The politicians don't. So that's out of the question in Sweden. We don't need coal power. Oil is, we don't have so much, and it's out of the questions. And then we have gas, natural gas. We have very little natural gas in Sweden. And then we have a big neighbor, which is the old enemy of Sweden, that is Russia. So that is the tradition that the politicians are always talking about the big threat from Russia. And then where does the gas come from? It's from Russia. So the question is, I heard one politician say, there is 2 problems with Russian gas. One is that it's gas, the other one is that it's Russian. This politician really likes to strengthen the military forces. So of course they always say that Russia is terrible. Anyhow, so in Sweden it's more like this, that we don't want to be dependent on Russia, and nuclear is too expensive. We don't want coal, and then you just count backwards, and then you get, okay, it will be renewable. And then from Sweden point of view, we have more hydro resources, although it's very controversial, so I don't think it will happen. We have the wind power, which is very big, and then we could have more biopower also. So we are very lucky in the world in order to make renewables. But then, of course, you get so technical, but on the other hand, what is much easier in Sweden compared to other countries is that we have this high amount of hydropower. But I will still show you where are the challenges, just to show you something about how it will look like. So what I have studied now, I have simulated an isolated Sweden, which is not correct, because Sweden is absolutely not isolated. We have, Sweden looks like this, that we have Sweden, the peak load is 27 gigawatt around. Transmission to neighbor, transmission to neighbors, 10 gigawatt. So here you see that I mean, we have a huge amount of trading, and I can absolutely say India will never get the same share of trading with their neighbors, of course. It's impossible, although a state may get it. So, but I'm looking on a isolated Sweden just to show you, just to illustrate how the challenges look like. So I have made a big report. It's in Swedish. So, okay, these are the details. I don't take that. This is just to show you how it may look like. This identifies something about how the variation is. And I'm sure that Sweden, if you have, let's say, if you had wind power all over India, then I think the changes will be smaller than in Sweden, because Sweden is a smaller country. But still, it will be nearly of the same size. I mean, India is bigger, but not that. I mean, it's, let's say, 3 times the size, as I understand, or 4 times. So I think that still, even if you have, it's a wider country. I mean, it's not that they are totally uncorrelated what is happening in different states in India. I mean, it's you have windy time of the year, not so windy time of the year. But this is at least as the meteorology looks in Sweden. So this is a winter week when we have a huge amount of solar, just to illustrate the problem. This is a winter week when we have, in reality, not so much solar power. The solar power on a yearly base, just to inform you that, and this is completely different for India. Solar power on a yearly base is 10% of the production. But in the winter, we get so much solar power, which is nearly nothing, because it's completely different situation when you see the summer, because all the solar power is coming in the summer. And then here we have combined heat and power. What we are doing in Sweden, on the other hand, is that we are burning waste. We have a huge amount of burning. That is the most profitable power source we have today. Because you have to invest in, of course, in this waste burning power plant, and waste burning you have in the cities in order to burn the waste, and then you at the same time get both electricity and heat for the town. This is very common in Sweden. What is interesting with these waste power plants is that they have a negative marginal cost. Reason is that you are paid to burn the waste, because you want the state, the town, of course, want to get, or the persons want to get rid of the waste, so they are prepared to pay to get rid of the waste. So you have a negative marginal cost, which is a problem, because if you come with your wind power and say that I have free wind power, and then they say that, okay, how much do you want to pay me to use your wind power? Because there are negative marginal cost in this one. Anyhow, so we have a lot of district heating, which are our power plants here. But here, what you see here is that here's a night between Saturday and Sunday. Here's the demand going up. This is, what is it, 2 weeks. So here the demand is going up and down, and here you have the night between Saturday and Sunday where they normally have the lowest demand. And at this time, you get a huge amount of wind power. And okay, and of course you cannot have, we are looking on isolated Sweden, this means that it's physically, of course, impossible to have more production than demand. So then here you have in reality to curtail the wind. So here you are curtailing the wind, or the solar power in the night here. No, there's no solar power in the night. So you curtail the wind, and then also in this situation you have extremely low marginal cost in the combined heat and power, so you are decreasing also these ones, which you normally don't do. And then the hydropower, you can never run the hydropower on zero, because you have some reservoirs, but still you have to have some water in the rivers, otherwise you destroy the fishery and so on. So you always have a minimum requirement in the hydropower. And this means that you have to curtail the wind in this situation. But then you see here, just 2 days later, here you have nearly no wind power. So what do you do? In Sweden, then we have, of course, this is the capacity in the combined heat and power, and then you have a little wind power here. Then you have the hydropower, but that is not enough from the capacity point of view, so need something more. And this, what I write here, is something more that we need. And this is the challenge, that if you take away, let's say you take away in India, let's say you take away 50 terawatt hours of coal power, and then you replace it with 50 terawatt hours of wind power, for example. Then the question is that, okay, but it happens that it's not windy. What happens? And it's the same that if it's maybe, then you can, the problem I think that if you have a huge amount of solar power, the problem will be the night. Because in the day, there's no problem in India to get the power because you have the solar power. But what do you do in the night when people are consuming and you don't have any sun? So I think that the structure will be the same, but it will be, if you go into details, it will be different. But you still have the fundamental challenge. If you replace the conventional units, which are giving a certain amount of power all the time, with something that is varying up and down like this, then the question is, what do you do when you have this low production for this new resource? And that is what you see here. So what we do here is that we need something more. That's the so-called deficit situation. Then what I do is that I have made the duration curve of this, stating how common it is to have this kind of capacity. And what I found out is that for Swedish case, because here you see that you need something more, and here is the more important message, you can say that this extra capacity, you need a lot. In our case, you have this 5 gigawatt. So if we replace the nuclear in Sweden with, then we will need, from energy point of view, then we will need 5 gigawatt of other sources. But then you must know what type of resources do you need, because this 5 gigawatt have a very low utilization time. It's used only, this 5 gigawatt that you need here, it's only used for 50 hours a year. Of course, you never build an oil fire station, you never build a combined heat and power, you never build a coal fire station or anything which is only used 50 hours a year. And all this power is only needed up to 800 hours a year. This is really the fundamental issue of how how should we manage this? You could have, for example, demand-side management. Okay, then the question is, demand-side management, yes. The question is, can you have demand management where people are decreasing their demand during 800 hours a year? No, probably not. So I'm sure that this last peak here, that is good to have for demand-side management. But then we have to, when you talk about demand-side management, you also have to go back here. Demand-side management very often looks like, okay, you curtail people, or you don't charge your car, or what you do. But the question is that here we are talking about that you need it for a rather long time in a row. So then you have to think about how does the demand-side management really work here? So you have to really go into details. I think demand-side but I think it's also important to remember that, because a problem when you see all these projects today with demand-side management, they think that they are solving the problem of today, and today you have the peak nearly every day. So then every day in the noon you disconnect your let's say your air condition during 2 hours. Yes, that's interesting, but sorry, but that is not how it will look like in the power system with 100% renewable. You will not have these regularly changes where you every day in the day peak. That is to manage the peak situation in a conventional power system. Then you can have this demand-side management. But if you want to manage the peak in a situation with high amount of renewable energy, it's different. It may be, for example, if I just take it without making any calculations, but if we say India, where it seems like the solar power is the big issue, then I think that it may be that if you take away the coal and you have a huge amount of solar power, then the daily peak is not the problem. Probably it's the night peak. The night will be the peak instead. And then the question, how do you manage the peak in the night? And then, of course, the question is, but then the question comes up, will you then have air conditioning in the night? It may be. But on the other hand, this kind of thing that you don't, then you, of course, if you have electric vehicles, don't charge in the night, charge in the day instead. So much discussion nowadays where people take these new things, demand-side management, electric vehicles, and whatever, and smart grids, and whatever they are calling it, and then they are applying it to the situation of today, and then they claim that this is a solution for the future with more renewable energy, which is not. So there are certainly challenges here, but you really have to go and think about how will it look with 100% renewable, and that is not the same as today and just a little more. It's different because you will have the peaks will be in another way compared to today, especially in if we take a huge amount of wind. That means that sometimes you have a peak when it's not wind, but then you don't have any problems at all. Look here, this is a very high load situation in the middle of the winter, and we get a surplus. But also in the winter, just 2 days later, we get a deficit, or what you call it. But then, of course, from this capacity, this is the capacity deficit. Here I assume that I just tried to say that, okay, we managed to peak with open cycle gas turbines. This is fossil fuels, but you could also have biofuel if you need it. It's a bit more expensive, but it's technically possible. It's not a perfect solution, but it's so doable. So you can, of course, you can solve the problem. You can have power plants here in order to do this. You can have open cycle gas turbines, and they will produce very little energy. So yes, this was the solution I had, and the cost for it is very negligible compared to the total cost in the power system. So of course it's manageable, but the question is then you have to get it working some way. So I think that there is a lot of, especially this with storage. This storage, I can tell you a little, just this with storage. There's a lot of discussion about storage, that we should need more storage, we need more pumped storage, and so on. Let's say we have a power system where the demand is today working like this. So this is demand. And then you have, okay, what I heard about India is that you have so much coal power, nearly everything is covered by coal, which I think is a bit strange. Do you also take the peaks with coal power? I think that's maybe correct, but I mean, let's say take a power system as, you can take Japan, for example, which is very much fossil. You have, here you have nuclear and coal, and here you have, let's say, oil, and here you have gas to OCGT here. In this power system, you get very high price differences. So the price will also if you instead look on the price, the marginal cost in the system will look something the same. Something like this. Okay. Assume that you in this power system, so this is let's say the price instead. Can you use storage in this system? Yes. Pumped storage. Is that good? Yes. What you do here is that it's very cheap power. It can go even down even further here in the night. It can go down. Let's say we take it even further down here, so the price go down. Let's say we make it like this. This means that in the night, the operation cost is very cheap, while in the peak middle of the day, it's very expensive. This is very common. I mean, this is how it looks in very many conventional power systems. So what do? Here you pump, of course. Here in the night, you can pump up the water. It's very cheap to pump up the water because you use only the fuel in the nuclear or the coal, and you pump up the water. And then in the day, you have this water, you have it stored up there, and you use it to replace OCGT. Okay, how many times a year do you do that? 365 times per year. Okay? And you have always big price differences. So 365 times a year, you can pump up, and then you can release it, and you lose, let's say, 20, 30% or something like this in cycling of up with the water and then down again. Or if you have batteries, it's the same type of thing. What happens if you have renewables? Completely different. In Germany, for example, where you have a lot of solar power now, you don't have the daily peak. Sometimes you have lower prices in the day than in the night. What is happening is that you don't get these regular price differences between day and night, which you have today. In a conventional power system, it's extremely smart to have storage. From the market point of view, it's very efficient because you can do like this. When you have solar power or wind power, it will be much more irregular. You don't always have this kind of thing. You don't have 365 times per year where you can go up and down and cycling. So you can do, you can, in a pumped storage or batteries or whatever kind of storage, it's an investment, which is of course very nice. And then you get the money back because you have the price differences. Very nice. But with renewables, it can be the opposite. You don't have the price difference because you have solar power. With wind power, you don't know exactly what will happen, and in some days you have, sometimes it's windy, sometimes it's not, so you don't have the regular changes. So I'm not so convinced, because people say that, yes, but with renewables you need storage. Yes, it's correct, but that doesn't mean that automatically it will be more profitable. You really need storage today. And today the storage is really fantastic, but people are not talking about it, because here you have regular changes every day. It's fantastic. And people say, for example, today that, okay, electric vehicles, it's fantastic, but then you should store it in the night because it's very cheap power, and don't store it in the day. Yes, fantastic idea. But, sorry, if you have a lot of solar power, please charge your car during the day, not during the night. Is your car at home during the day? Maybe. It depends on which type of, how it works. So I think that there's a problem that people have these solutions for the future, electric vehicles, charging or storage or whatever it is, and then they say that, yes, we need this flexibility in the future with larger amount of solar and wind, but they apply it to the system of today, and then price difference of yesterday or something like this, and see that, okay, look how much I can earn on the store on this one. Yes, but sorry, this is for today. This is not for tomorrow. What happened? Something. What is most complicated? Is it power system or IT? I don't know. The combination. Okay, so now we come into the other situation. And that is, in Sweden, now we have 40% of yearly energy from solar and wind power, and it is a summer day in Sweden. And then it looks like this. First of all, I think it's important that you see the solar power, how it is changing. And I think that this is around the same. It will probably be a bit broad, because it's, the question is this a sharp peak or not? Because it's going up a lot and then it's going down. Sweden is a country like this, while India is a bit broader like this. So if you have solar power in India, I think if you look on total India, the solar, I think you may have a time difference. What was it, 2 hours or maybe 2.5 hours or something. So there is a slightly time change, which means that you get exactly, if you have everything around just from north to south like this, all the solar panels goes up at the same time. But this is, you get a slightly more difference, but not that much difference, I think. So it will look something like this still, that you have in the day, you will have power, but not in the night. This means that you will get ramps here, and you will get ramps here, and that has to, of course, be compensated in some way. The important thing is that sometimes, and the benefit, of course, of the solar power is that the solar power has around the same shape as the demand. But what you see here is that when you get large, and remember, this is only from, in Sweden point of view, this is only 10% of the Swedish power. I think that the solar power changes will be higher than the demand changes, and I think it will be like that in India also. I have not gone into the details, so if you have, let's say, 30% of energy in India from solar power, just take something, then I think that the ramps of the solar power will be higher than the ramps of the demand, just to have some kind of feeling for it. And this means, of course, that what the other power plants is that in the morning they should ramp down. So I think that you will get to the peak load in the night, and then you will get if you have a large amount of solar power. This is, of course, varying over the year, because you have the monsoon period when I sure that there's not so much solar power that is really coming down to the ground. I don't know the details, but I think that very often when it's very sunny, it's good, but I think then the peak here is more. So the challenge is then that in India you will have, let's say, lower consumption in the day from the other power plants. So the power plants have to cycle in another way than they are doing today, which of course has to do with this when you are coming with demand-side management and so on. The challenge is also, at least in Sweden, it depends on how much solar power you will have in India, but at least in Sweden, what will happen is that you can have low demand, and then at the same time it's very windy. Wind is, from that point of view, a bit more complicated, but it depends a little about your situation, because wind doesn't care about if it's day or night or something. They don't look on. There is seasonal variation of wind, of course, but otherwise, at least in Sweden, we don't have any regular winds that is going up in the morning or something like this. You may have that in some areas. I don't know about India and here. So the challenge is that you get this surplus. And that is what you see in nearly all countries. What I know, you have all countries with large shares of wind power. You have Ireland, you have Denmark, you have Texas, you have Spain and Portugal. All these countries have large amounts of wind power. Germany is well known, but in reality, I mean, if you see, they are extremely interconnected, and it's a big country. So from the share point of view, that is not the way I see it, the most interesting country. But all the countries with high share of wind power that you see, both in, as I said, Texas and some European countries, there you curtail wind. This is for Sweden then, and we have 40% of the yearly energy from solar and wind power. And of course, so this way you cannot run it. This, of course, it's technically impossible. You cannot have more production than demand. So in reality, you have to run it in this way. So you have to, in some way, curtail or export or make hydrogen or whatever you are doing. You in some way, you get a surplus that you have to do something around. But you can never have, or never and never, that's a question, of course. Here, you have to have some kind of margins. Because what happens, for example, let's say you suddenly get a problem somewhere. You get a problem in a transmission line, so you don't get all the wind power from a certain area. Then you have to have a margin. So some power plants have suddenly to increase. I mean, just because you get a problem, it will not be more sunny or more windy, of course, exactly at that millisecond. So you have to keep a margin. One way of margin is to down-regulate the solar and the wind power. And here, of course, if you have solar power which is distributed to all the people around that, how do you really control the distributed solar power so they are keeping a margin which is used if the frequency is changing or something like this? Technically possible, of course, but we are not now talking about to have contact with 100 units. You are talking about having contact with millions of units or something. So it's, of course, a challenge to really down-regulate in a smart way from the power system if you have distributed. If you have big farms, it's easier, of course. But if you have distributed, which will probably happen in India if you raise the tariffs, then, of course, at some situation, you will get this, you will get automatically a huge amount of solar power. That is what is happening currently in southern Italy. There the solar power is cheaper than what people are paying for their electricity. So they start to buy solar power just because it's profitable. And I mean, at some, I don't know anything about the prices and the costs and the tariffs in India, but I think that if you are going towards a more liberalized market and you, at least the consumers have to pay what the power costs, then of course you will raise the tariff slowly, and then of course since the solar power is decreasing in cost, at some situation you will get this. The question is then how to handle this from the system point of view. So this is the surplus, and this is the surplus that we will get in Sweden. We can get a surplus of 9 gigawatt, which is a lot. The important thing is here, this is of course can look different in different countries, but this is the way it looks in Sweden. It's extremely few hours. So you have and this is of course, you get the surplus of up to 9.5 gigawatt nearly. But the last 2 gigawatts here is only for, 20 hours a year. Of course you curtail. You don't build a transmission line in order to be export to use it during 20 hours a year. You do not buy electrolyzers to make hydrogen just for 20 hours a year. Electrolyzers are very expensive. There is a lot of this discussion of making hydrogen. You can make hydrogen, you make electrolysis of water using electricity, and then you get hydrogen, and then you can use hydrogen later in a fuel cell or in some way. The problem is that then you have to make this hydrogen, and then you need electrolyzers that are separating the H and the O in the water, and these are very expensive. It's the capital cost that is important, is high there. So here you have, so I think you will curtail, but still the question is that you will get the surplus. The question is how to use the surplus, and I think that there are discussion of using it, and of course you should use it if you can, but the way I see it is that use it if it's economical. You should not buy a lot of things like this just to use the surplus. I mean, then you can use this money to do something else, hospitals or whatever. I mean, there are a lot of need of money in the society, so why should you use it to build a lot of technological things which are not smart from the economical point of view? So there will be curtailments. But then, of course, when you start, and then you also have this with 800 hours a year. Of course, when you come down here, if you have some kind of surplus which is used a rather long time per year, then you can start to think about should you have batteries or should you have big, but I mean, these peaks where you are only using the surplus during 20 hours a year. I mean, I showed you this earlier. Here you have a surplus, you can call it, which you are using for pumping. This is every night, 365 times per year, and you can pump during 4 hours. This means that you are pumping during, I mean, it's a huge amount of hours per year. Here I'm talking about a surplus which you can get 800 hours a year, and it's very irregular. You don't have it every day like this, then it's simpler. So sometimes you have a lot of surplus, and sometimes you don't have any. That's what you can see, for example, here. That here you have a surplus, then you get a surplus here, but here is no surplus at all. And that is, of course, a very big difference compared to the very nice, from power system operators' point of view. That's why people, of course, are like what they have, because this is so easy to handle. You know how to pump and so on. In Germany, I heard, that is very interesting, that was heard people pumped storage they have a lot of pumped storage in Germany, but the economy is worse now with more renewable than it was before, which is not so strange, which is absolutely natural. Because what have happened is that sometimes in Germany it has happened in some situation when you have low demand and extremely sunny all over Germany. Then you have lower prices in the middle of the day instead of in the night. And if you have that like that, then the question is, why should you pump? You should pump in the day and release it in the night. So I think that one possible project, of course, for you is that how to use the pumped storage in India when we have 30% solar power. That is, of course, and then the question is also, where's the storage? What kind of grid do you need for this kind of challenges? I mean, there's a lot of interesting projects here. Fantastic future. Okay, so this is the fundamental challenge this with surplus and because I think there is too many projects where they look on the today situation to solve the today situations with solutions that is said to be used for tomorrow. But if you study tomorrow, then also look on the assumptions for tomorrow, not for today. Okay, so then you have need of extra capacity, import, I write. This is interesting for perhaps an Indian state, but not for India as a country. And then the same thing with the surplus. It may be exported, or if you have a certain state, then of course. But if you see it from the national point of view of India, then of course export and import is not a solution. You must have some kind of technical other solutions to in order. But in Europe, this is very much discussed. So in Europe, there are very many new transmission lines planned. And everyone is, of course, looking on the Nordic hydro, because we have 45 gigawatt of hydro in the Nordic system. Right, it's here. Nordic system, 45 gigawatt of hydro. And that is that's why, for example, Norway, for example, they are connected to Denmark with when it's very windy. When it's very windy, you can. So here we have Denmark, and then there is a line here, a DC line, HVDC to Norway, and here we have Norway. And then we have Denmark, very windy, means low prices, means Norway import. And then if we have the opposite, Denmark, not windy, means high prices, means Norway export. So Norway loves the Danish wind power. They import cheap when it's a surplus, and then they export and earn a lot of money. It's more the same type as pumped storage. So you can see the Norway as a sometimes Norway try to make adverts for themselves as being the European battery, which is because they have a lot of this kind of thing. Just to say something about storage. This is, of course, the North European perspective. If you have a battery, car battery, they are normally 12 volts, 60 ampere hours, means 720 watt hours is equal to 0.72 kilowatt hours. Okay? It's one car battery. Then the lithium batteries are a bit better. Anyhow, this is the size. 1 terawatt hour storage is equal to 1 billion. Now we have to be specific here, because billion is different. United States and UK, I don't know which billion you use. We say like this, 1,000 million instead. 1,000 million kilowatt hours. Okay? In the Nordic system, which means that 1 terawatt hours of storage is more than 1,000 million. It's 1,300 million batteries. In Sweden, in the Nordic system, we have Nordic system, we have 120 terawatt hours of hydro storage. Then sometimes people say that, yeah, you know, with more renewables, we need batteries. And I just wonder, can you please motivate that? because that is not so easy, because you have to look on the total storage in the system. Yes, there is a discussion. Yes, batteries can be good, but you have to compare it. I have not seen anything, because I know that you have pumped storage here in India, but I have not seen anything about the sizes. But I think it's important to make some kind of rough, when I draw these kind of curves, how much storage do you need? And because storage is certainly interesting, but it's not an automatic system. Okay, this I don't have to go into. Okay, now I will go into a little, because a challenge that will happen in the Nordic system, and I don't think it's, if I try to understand about India, what I understand is that the wind resource is in the southern part, not so much, but the solar potential you probably have all over India, although they can have slightly different weathers in different seasons. But on the other hand, you have the cities which are consuming daily, and these kind of cities, they are consuming a lot. And of course, if you have solar power in the day and you don't have the solar power in Delhi, this means, of course, that, I mean, if you take away coal power plants that are close to Delhi, and then you will have the solar power spread out all over India, then of course you will get large import from the solar power that is outside Delhi when you are in such. So you, of course, you need some kind of grids. And the grids must, let's say, transport things. In Sweden, we have something called voltage stability, which I don't understand. I don't think voltage stability is probably a big issue currently in India. The reason is that voltage stability, you have a problem when you have long transmission lines. When you have a significant reactance on these lines, then you have a problem. In Sweden, we have a long transmission line means that you have, here you have R plus JX, and then you have a long transmission line. In Sweden, these lines are so long, so in reality it's the reactance that is limiting how much power we can transport on this one. So in Sweden, around here, we have all the parallel lines are in reality series compensated. I don't know if you have that in India. I don't think you have that, because I think that's, I don't know, but I assume that in India you have more, since you have coal power nearly everywhere in the country, and they are very much supplying the, let's say, the demand around that area. And that means that the distance from the generation to the demand, I assume that is much shorter than in Sweden, where we have, as I said, that the length of Sweden is as from Allahabad to the southern Tamil Nadu, as I understand. And so it's rather long. I mean, the power is very much often transmitted 1,000 kilometers or something like this. I doubt that it's so common that to transport power so far in India. The problem is that transport over longer distances, you get voltage stability, which is the limit. That you can solve with static VAR compensation or capacitors and so on. But it's the voltage stability that is the... So Q control is very important in Sweden. It's not only to keep the voltage, it's also to keep the transmission capability. We need the reactive support. And this is, of course, the challenge. Let's say we have, just to take an Indian example, I don't know anything about Delhi, but I just assume something here. Let's say that this is the Delhi area, and then you have some power plants like this. I assume that you have them rather close to Delhi. They are not outside. And then you take away these ones, which is of course nice, and then you have solar power, and solar power is of course everywhere here around. I mean, you cannot have so much solar power in Delhi because you cannot have it on the roofs, but I'm sure that these solar power plants will not cover the demand in Delhi. And this means that you will have more transmission. And it may happen that it will be over longer distances. And then, of course, it may happen that you also will reach something called voltage stability issues. But I don't know anything about that. But that may happen because, and what is interesting is that it's changing a lot. Transmission will change a lot. Let's say that this is the solution. You take away some coal power plant in order, and then you replace it with solar power around many sites like this. then you will get in some situation a huge amount of transport in this direction. The question is, on the other hand, what do you do in the night when it's not so sunny? So then, of course, you have to manage these situations. Then perhaps you can import in another way. So you will get much more changing flows. And sometimes you will get a huge amount of power from the solar power when it's a high resource. And then when it's not a high resource, you will probably not have the backup in the same places. You will probably have the backup somewhere else in other power plants. So you will get much more changing flows in the system. And then you have to manage the transmission system in another way. You cannot have a static control of how to operate the system. In the day I do it like this, in the night like this. It will be that, okay, when it's sunny there, I do like this, but on the other hand, if it's windy, I do it in the following way. So it will much more changing flows in the system. And then, as I understand, what you are doing here is that you are looking on these PMUs, for example, phase measurement units, where you are studying this in the transmission. And I think that the challenging thing is that what I think is, this is a bit also connected to why universities are needed, that if you have a power system which looks around the same all the time, we have the coal power plant, night, day, night, day, and so on, then experience is very good. You can ask the guys of my age, yeah, we know how to operate the power system. They, of course, say. The problem is that in the future, you cannot say that I know how the power system works, because it completely depends on what is the solar forecast. You need more algorithm. You need to plan. It will be more stochastic how to operate the system. So, of course, you really need a very long experience in order to say that you know how to operate the power system. So analyzing methods, I think, will be more needed in the future because it's so stochastic. Okay, so more transmission will be required. But here you have the challenge. It will be lower utilization time. I know that you are building a new HVDC lines in here. I don't know, but I assume that they will be used very much in probably one direction. But I'm not sure. It may be that, for example, you feed it down. But if you have what is happening, and that is a challenge in itself, and that is that there is a risk that with the new situation, you need transmission, but the utilization time will be decreased. Because if you have a very sunny area, of course, sometimes you export sunny. And that is, of course, not during 8,700 hours a year. It's only in a much lower amount. So this is, of course, a challenge when you start to motivate your transmission lines that they will not use so much. And then here, this is, of course, we can just change the nuclear to coal here to talk about India. A challenge to identify future transmission capacity. It is a challenge, of course. Let's say we see this future with much lower amount of coal power. Probably, I assume that they will start to try to get them out of the big cities, because that is, you have the bad air and so on. So then, of course, I assume that that is the first step, to try to get them out there or replace them with clean one. That is also a possibility. But the question is, when the solar power comes in, will it replace these ones? And I think that this is at least what is happening in Europe. You don't want to have the power plants too close to the cities. And then all the renewables will not be in the center of the cities. They will be somewhere else. So that means that you need more transmission. So and I will just show you a little bit when I have studied this for Sweden, how it will look like. So the challenge, I don't know why I wrote this here, but the challenge is very much to identify how you, the problem is very much how to get a good model of this. If let's say you want to study this kind of issue, you want to study India with 40% solar power. Okay, then you should have a good model for India for solar power for the future. Where is the load, where are the current power plants, and so on. And as I understand, you have the same problem here as we have in Sweden. That is that it's extremely difficult to get exact data about how the system looks like. So you need to have some kind of representative system and so on. What's the time? I should talk to 11. That 11, not your 11, not the correct 11. This is that 11. The wall. What would we call it? The wall 11. Okay. Okay, so this is how it can look like. I just studied one of these bottlenecks. I studied a certain situation for Sweden. As you see here, you have the solar power, and then you have the wind power. It's the difference here. So here you see the solar power. It's coming up in the day, and then you have the wind power, and it's depending on here. It's not so windy at all, but here is a lot of wind. And then you can see how the transmission is varying. And that is much more irregular than it has been earlier. And then, of course, when the transmission is varying a lot, then, of course, you get also varying voltages in the system, which you have to manage in a good way. Technically, of course, possible, but it's important to see that if there are rules today how to use it. And then, of course, what can also happen is that you will get, what you see here is that here you suddenly got a peak, which is very rarely. And this is one of the challenges, that you can install a lot of transmission, your transmission needs. In this case, I didn't have a transmission model. I just have area modeling. I have a model of what is happening here, a model of what is happening here, and happening here, so on. And then, of course, I just calculate how much will the changes be in this one. And then I can say that, okay, how much transmission do I need? And then I can say that I need so much transmission. Okay, do you mean that I should build these extra, which is, 800 megawatt of transmission, which is only used during 2% of the time? No, that's not rational. And this is, of course, a fundamental issue. How should you define the dimension your transmission? Because, of course, and if you don't have transmission, how do you then handle the balance? Because then I cannot handle it as good, because here I assumed a certain amount of operation of different power plants, but here, if I don't have the transmission, I have to, in reality, if I cannot transmit like this, then I need more power in this area if I cannot import it from another area. And these are the issues. If you take this example of Delhi, for example, that we take away the coal plants and have the solar power outside here. Okay, should you really dimension it this? Perhaps we should keep some of the power plants here. But then you must also look on what is the utilization time of these power plants. It's perhaps only 10 hours a year. Then perhaps you can have demand-side management just because of transmission issues. So there are a lot of interesting issues. As you see here, I'm talking about 20 PhD projects, no problem. And this is another situation, and that is what you have here. This is a Swedish case, but it's a bit, we take I don't know anything about Delhi, but just an assumption. Today I assume that Delhi has this kind of consumption. What is happening in Sweden, it looks like this, that southern part of Sweden is mainly a consumption area. We have some power plants, but it's mainly a consumption area where the power is imported from this area. It comes down like this. If we have a huge amount of wind power, let's say some offshore power plants here and so on, and some more solar power, because here's the area where you have a lot of people. So here, if everyone is starting to have solar power here on the roofs, this will be a production area. But it depends on how it looks like. And here you can see that today, this transmission is dimensioned, so you are sending power in this direction. You are nearly always sending power in this direction, and the voltage control is based on that, and so on. So you get voltage drops in this direction, and so on. What will happen if we have much more solar and wind power? You get a changed transmission. Sometimes you are sending 2,200 megawatt in that direction, and sometimes you are sending, 3,000 megawatt in the other direction, depending on that. When it's very sunny or very windy down here, you are sending power in the other direction instead. So you get much more varying flows depending on the situation in the system. And then, of course, you have to dimension your power system based on that. And this is just another one. I took the January week, and then yes, it looks like this. So it's the same thing, that here we are sending, suddenly, earlier it was a summer week, yes, now it's a winter week. And here we are suddenly sending more than 10,000 megawatt, 10,500 megawatt we are sending here. And I'm sure that 10,500 megawatt, that will only be for some hours a year. But then sometimes you are sending also, what is it here? 4,000. This is very windy, and it's probably a night, and it's very, because in Sweden it's also like this, and it's probably, if you have wind power in India, sometimes it's windy here and sometimes it's windy here. So if it's very windy here and you have a night and you are not consuming so much, then of course you are sending power in this direction, which is extremely rarely in Sweden, since we normally have the power production up here and sending in this direction. So this is what is happening. It's not only the power that is fluctuating. Of course, based on that, also the transmission will be changing in a lot of different directions. Sweden is, from that point of view, a bit easier, I think, to simulate than it's possible. Because India have a lot of states, you perhaps have data per state or something like this, but it's a meshed system all over India, so you need some kind of grid model. Here I can only have a simplified area model in order to see the data. Just one interesting thing, I don't know if you have it in India, but in Sweden we have data per area per hour available on the internet. You can just get it easy. So everything here is based on officially available data. You can download it from Sweden if you want. Not so interesting for Indian analysis, but so we have the wind power per hour in this area. We have the demand per hour in this area, and we have it per area available for, what is it, 10 years now, I think. Because this is an extremely good source if you want to make some analysis of this. Okay, so then here we came into this issue, that is the transmission we have here. So I made this duration curve of this, the transmission. How much in the future, if we have a huge amount of solar and wind power, how the transmission will look like here. And then the question is, today we can transmit around 7,000 megawatt. But when I'm simulating the future, if we should, then we can say that the transmission need is, what is it? 10,426 megawatts. 10,500 megawatt is needed if you really want to transmit everything. But the last, it's very good with this duration curve, the last use is only for, what is it, 200 hours this month. So I think that it's profitable to build more lines, but because there are also planned lines like this. So you will build lines, but of course I'm sure that you should not build lines, you should never build a transmission capacity which only use 2 hours a year. And that is, of course, a discussion, how many hours a year should it be used in order to make it profitable. On the other hand, if you don't make a transmission line that is covering the need, then the question is, how do you manage the balance here? Because in the first assumption, I assumed that it will be possible to import. But if I cannot import, what do I do? Then, of course, I have to have a power plant or curtail consumers or whatever. I have to have a balance. There will be a balance. So if you are not building that, you have to increase the production in the receiving end. If you are not, let's say, building, you can call it enough capacity. Let's say Delhi, for example, you take away these ones and then you replace it with solar. These with the capacity that is needed in order to supply Delhi. Then, of course, you need some kind of local power plants anyhow if you are not dimensioning for the peaks. So you still need that. But I think that, of course, you need transmission, but the problem very much, I think it's in India is of course one challenge, but it's the same everywhere. The problem is that you don't need in the future. You don't need you don't know what is happening in the future. This is a stochastic thing. I mean, let's say that we plan to do this, just as a case. We take away these ones, and then the question is, okay, what is the demand in Delhi? Okay, we are talking about 5 years ahead or 10 years ahead. Okay, what is the demand in Delhi 5 years ahead from now? What is the peak demand? You don't know that because you don't know so much about the economic development, the use of air condition, and so on. So and then of course when you dimension these lines, then how to dimension them when you don't know what will happen? I mean, it is a problem to do that anyhow. So you have to have margins, or you have to have methods. If the transmission is not enough, then you have, of course, to do something. the capacity is available, then of course, and this is of course, the question is what kind of limits you will have. It may be, what I don't know. Just about the stability, I don't know, for persons are working with stability. When you have a power, let's say we have this line here. You can have different kind of, when you want to transmit power here, P, the maximum, you want to maximize it. You can have different limits here also, of course. You can have voltage stability. Means build SVC of some kind. I mean, you can solve the problem, and that is what is happening right now in Sweden. We have voltage stability as the limit, but if voltage stability is the limit, you can solve it by having reactive support in different ways. So on the other hand, then you have solved that problem, but then you get the next problem. Angle stability. That is the next step. And then that is solved with very much control science. Control or phase measurement units or this kind of things. But if you don't have that problem and you don't have that problem, then you get a called thermal stability. Thermal stability means build lines. And you have a different kind of methods here. You have high current lines where you can manage the and then of course you have also transient stability that could which is closely related to this one. You have the voltage stability, angle stability, the transient stability, which is linked to this, and then you have the thermal stability, or current, you are hitting the current limits. But current limits for overhead lines is mainly that they are sagging like this. And the sagging, it depends on the temperature. That is better in Sweden than here, I can say. In Sweden, the high consumption is in winter, and then it's extremely cold, -20, then you have perhaps the problem. But then you have a nice cooling of the lines. At the same time, the big problem may be when it's very cold and very windy. And when it's windy and cold, you are cooling the lines. Here, on the other hand, which is a challenge in more, it's the same in US, for example. And that is that here the problem is probably when it's very hot. And then the lines cannot manage as much current as when it's cold. So here, I think, here you have you can call it, in Sweden, we have a good correlation between the demand and the transmission capability. While here, when you have countries, you have the benefit of solar power, but on the other hand, you have the problem that when it's very sunny, you get much solar power, but on the other hand, then you have probably the high demand. And then if it's very far away, and this, then of course it's probably very hot, so then the lines are sagging easier. So which is the problem in itself. They are not cooled down. But then you have different types of solutions here of having high temperature lines that are not sagging. I don't know, perhaps not everyone has worked with that, but the problem with transmission lines is that the problem with transmission lines is that what is happening is that then when it becomes very hot, they are going like this, and then of course you can have a tree or a person there, which is not so nice. And then of course, so that is normally the problem for transmission lines, that they can. But there are, as I said, some solutions. But of course there are limits. You can raise the voltage, you can do some changes. In Sweden we have, for example, 220 kV lines, and some of these are changed to 400 kV lines, and then of course you can transmit more, but then you need more isolation distance and so on. So it's voltage stability, then static var compensation may be enough, but that is happening already in Sweden, so we are coming with a lot of voltage stability issues. And then so nowadays, which is new for me, I heard it just 2 weeks ago, that it seems like in Sweden we will get the angle stability with rotor angle stability while you oscillate the different synchronous machines. On the other hand, if you don't have so much synchronous machine, how can you get oscillations? So that is, of course, a discussion that will happen in the future, which we are discussing. In Sweden, there is also a discussion of changing AC to DC, which you can do. There are technologies for that. I think it has been done. You can use, perhaps, but I have not heard exactly how it is. But there have been a discussion that you change these AC lines to DC, and then you can transmit more. But from thermal stability, I wonder, because that should be the same current limit. But but it has to do with the voltage and so on, how to handle this. So that is a discussion of doing, of course. But this is only, I mean, DC lines are normally very profitable if you have very long distance. Because the problem is with DC is that the converters are rather expensive, while the line in itself is cheaper. So if it's very long, then of course it's cheaper, the transmission, but that is compensating the cost for the converter. So it's a very short line, you don't earn so much, but if it's a very long line. What I heard earlier was, I think the limit was 600 kilometers or something like that. So it must be rather long, I think, in order to be profitable. It may be that this is a good solution here, I don't know. And then, of course, this optimization here, how to handle this, which is, of course, everything is an optimization problem, since you always want to do everything as good as possible. Four minutes left. Okay, so now I will go into this, the more details about especially the balancing here, because then we are talking about this keeping the continuous balance. And the big challenge is, of course, continuous balance is in different ways. So I will start now a little and I will continue then. These are, let's say, the challenges in the balancing. You have the inertia first. Perhaps, I don't know if everyone has studied power system stability, but I will go in a little to this at least. You have the inertia, the primary, that is what is happening within seconds. Then you have the primary control in the power plants. Secondary control in 5 to 10 minutes. Then you have the tertiary control, which is more, this is automatic, physically, this is physical, this is physics, control science, manual normally, and then you have the intraday trade, and then you have the day ahead trade and so on. I will go more into the markets later. And then we have in the Nordic system, since we have so much hydropower, the weekly planning and yearly planning is also very important. I think that here in India, I assume, since it's not so much hydro, it's probably the maintenance planning that comes in here. We should not have maintenance on all the lines at the same time, not maintenance and not closing down the coal power plant at the same time, so you should manage one at a time and so on. So that here in Sweden, the yearly and weekly planning is very much hydro. Should I use the water now, or should I store it to next week or next month or something? So in Sweden, this is very much hydro planning, but I think that here this kind of thing is more maintenance planning of grids and so on. Synchronous power system, it was a bit unclear if the Indian system is one synchronous system. Are there only AC lines connecting everything from Mumbai down to Kerala? Are there transmission lines going all the way? AC lines? Okay, so exactly the same frequency. You can phone your friend and they can and say that, yeah, now it's 50.02. And they say, yeah, it's 50.02 here. It's exactly, and then you can have small variations. So you can phone them and ask them if there are some kind of stability problems, because then you, it's increasing. And you say it's decreasing. We have oscillations, you can say. So okay, you have the same frequency. So it's a completely synchronous system. Then I don't have to go through this. This is a bit basic, but this is, I mean, the important thing is that when we are talking about keeping the balance, production is always equal to consumption, and exactly when a bulb is lighted, some generator will deliver the power. Exactly when a power plant is stopped, the corresponding power will be, not has to, remember, will be. Exactly when a bulb is lighted, some generator will deliver the power. It's not that they have to deliver the power. They will do it because it's physics. Well, exactly when a power plant is stopped, the corresponding power will be delivered from another power plant. I should have 1 point extra now, I see, since I'm talking about wind power. Exactly when wind power is decreasing, exactly at that millisecond, the power will come instead from some other power plants. Or exactly when the wind or sun is increasing, some other power plant will decrease their production. But that is, of course, a system balance in itself, because it has to do with all the other changes in the system. It may be that when I put the bulb on, someone is taking his or her one off. 1 minute too much. So now it's 1 past 11 in the strange watch. Okay, so now we have a break then. Okay.